All right. Good morning again. We will come back, or we will now come back to this flowchart and how to analytically solve a differential equation, right? So for now, what we're going to do is we're going to finish, or we've finished already, right? Sorry, we've finished already this part of our flowchart, right? If we know that it is first order, it's a first order differential equation, you can use many different techniques. I've taught three so far, right? Those two, the homogeneous coefficients and Bernoulli differential equation, that will be more in depth in your Caling 3, which we've already finished, right? So this is again more of just like a review, right? What now if the order of your differential equation is higher than 1? What if it's now second order, maybe third order? What we're supposed to do first and foremost is just to create, or rather to use, right, the differential operator, the DO. Right? In this case, we will now go on to the DO. This is the focus of today's of this video, right? And we will define a differential operator very literally. This is an operator much like a plus sign or a minus sign or a multiplication sign, and it has its own, shall we say, rules, right? We define an operator to be something like this. When you have the letter D, what you're assuming, or what you're rather saying, is that this is just the differential, or rather the derivative with respect to some variable. Say, for example, X or maybe T. Maybe T would work. And the thing about this differential operator is that it helps us understand what we should do next if ever we see ourselves in a situation that is higher order. Now, I did say earlier that this is applicable for higher order differential equations. But now, I will tell you that it's actually applicable for just literally any order of differential equation. Say, for example, this one. Oops. Say, for example, this one, we will make this just a very quick, right, example. dy over dx minus y is equal to 0. This is technically a first order linear differential equation. So honestly, if you want, you can solve this using the linear differential equation using the integrating factor here. But in this case, I would like for us to try and solve this using the differential operator, because, well, it's a bit of overkill, but it's supposed to be a way for us to understand how it works. This thing you can just write down as the derivative of y. Minus y is equal to 0. And now we have to understand first that not only is it important that this is a first order linear differential equation, it's also important that this is homogeneous, that this is equal to 0, that the right side is equal to 0. So now what we can do, and this seems very wrong, is now we can group out our y. We will have d minus 1 is equal to 0. And furthermore, what's even more wrong is that if we do this, right, you're not supposed to cancel out variables, because what if they contribute to a division by 0? It doesn't matter here. What matters here is that we get the value, quote unquote, the value of d. Very clearly, the value of d in here is 1. This 1 will now correspond to a solution, that you can already create. Right? I can already create the solution, which is y is equal to a, right? A and c and whatever, right? That's possible. So honestly, c can work. Ce raised to whatever this is, whatever this value is, should reflect there, right? M. Okay. So what will literally happen is just ce raised to x. So you might be wondering, well, is this true? And you can try to check it using this equation, but yeah, this is true, right? You can also get this using the linear differential equation. You can also get this through the integrating factor, but that is supposed to be how we solve this. That is the differential operator. That is the power that it can bring. It can bring differential equations into algebraic equations, which is very cool, right? Especially in this scale, but it is very limited in that you can only apply this for homogeneous, right? Homogeneous differential equations. So now let's try it out with this. 2 times the second derivative of y with respect to x minus 7 times the derivative of y with respect to x plus 3y is equal to 0. And we can see here that this is just the second derivative of y. This is not 2dy. Okay, this is not 2dy. Instead, what this is 2 times d squared. D squared y minus 7 dy and then plus 3y is equal to 0. Now, as we can see, it's d squared because you literally are deriving it again. It's the derivative of a derivative of y, and because it's written down this way, what you can do is just square it, right? Quote unquote. And now what we can do is just like the same thing we did earlier, we can now factor out our y and we will get 2 times d squared minus 7 times d plus 3 is equal to 0. And then you can cross out your y. And in this case, do whatever you want, right? But we have to find our value of d. In this case, right, what you can do is you can quadratic equation this. You can do whatever, but I prefer that you just factor, right? 2, 1, 1, 3. If we do this properly, -1 and -3, they become +3 if you multiply them. 2 and 1 become 2 if you multiply them, and you will have -1 and -6. If you add them together, you will get -7, which is this thing. I am just putting in here a crisscross, the crisscross method, right? The crisscross method. What you do is you multiply this, and you're supposed to add them. And this is a kind of a trial and error method where you're supposed to get, if you're successful, this second coefficient right here. And now, how do you read something like this? Just this, right? Okay, it's raining again, right? So now what we can do is we can say that this is just equal to 2d minus 1 times d minus 3 is equal to 0. And then you will get two values in here. Two values which correspond to d equals 1/2 and d equals 3. What will happen then? Well, the answer in here would require two arbitrary constants, right? One for each value that you bring. And that is why I can also accept in here if you say ae raised to 1/2 x plus be raised 3x, right? As you can see, each value, right? Each value that we've assigned has an arbitrary constant, right? And that pertains to the order, right? If you have a first order differential equation, you'll only have one arbitrary constant. If you have a second order differential equation, well, you will have two arbitrary constants, so on, so forth. Okay, that is for our first example for our differential operators. You can see it's very easy, and we're skipping a lot of things here because, well, we're engineers. We're not mathematicians. We're here to, shall we say, take advantage of the exploits that mathematicians have seen before, right? Way, way before. Okay? And actually, for number 2, what I'd like to do for number 2 is change a little bit here, because in here we have what we can basically say two real solutions. But sometimes that is not the case all of the time, right? I will do a little bit of a detour, right? I will provide more examples. What if now what we see is y prime prime plus, right, 4y prime plus 4y is equal to 0. And again, right, sounds not very daunting, right? But in this case, what we're supposed to do now is something like this, right? Just like before, we apply the differential operator, d squared y plus 4dy plus 4y is equal to 0. And again, we can remove the y, and then we are left with d squared plus 4d plus 4 is equal to 0. And again, we can cancel the y. We will be left with d squared plus 4d, plus 4 is equal to 0. And hopefully some of you already recognize this. This is just d plus 2 squared. That does not look like a d. D plus 2 squared is equal to 0. And in this case, you might say to yourself, okay, so the answer here is negative 2. But this is a second order differential equation, right? What am I supposed to do with that information? How are we going to go past this? Because we know, right, in our general solution that there needs to be two arbitrary constants, but we're only getting here one answer. The thing is, you're not actually getting just one answer, even though we understand this is two repeated, or rather one repeated solution. There is still another copy of your 2. So you might say to yourself, okay, all right, yeah, I get that, right? You're supposed to get in here negative 2 twice. So the answer is something like this. Y is equal to a e raised to negative 2x plus b e raised to negative 2x. The thing with this is that this very easily falls apart because of the fact that, well, now I can just combine a and b, right? They have a common factor, which is e raised to negative 2x. What's stopping me from just combining a and b to form just one, right? Just one arbitrary constant. Well, what's going to stop them from combining is that if you introduce what we call a linear combination, this is the same kind of linear, this is the same kind of adjective that we would see, or that we have seen before in our earlier discussion of linearity, right? You introduce a linear combination, or rather, another word or another way to phrase it is that you prevent them from combining by including now an x, right? The more copies you add, say for example, you got negative 2 3 times. Well, you will add in here now cx squared e raised to negative 2x. Say for example, you got another copy, then that will be dx cubed, right? But whenever you have a repetition in your answer, the clear answer should just be you introduce what we call a linear combination. Make sure they don't combine. Make sure they do not combine. That is the rub, right? That is the rub. Okay. All right, so that is our general solution. Right? That is our general solution. Now, for this number 3, I can see that my examples are not very great. Let me try and edit this a little bit. I will make this 6y. Then I will make this 13. Yeah, maybe 13. 13 would be good. Yes, 13 would be good. Okay, now let's turn this into its differential operator form. Again, d squared y minus 6 dy plus 13y is equal to 0. All well and good. We can remove the y. And honestly, at this point, we can just go on straight to our answer, right? Or rather, straight to what we need to do, right? 6d plus 13. In here, the crisscross method will fail, right? 1, 1, 13, 1. You will never reach negative 6. So, well, we're going to have to do it the hard way, right? Which is the quadratic formula, right? Negative b, right? Negative b plus minus the square root of b squared minus 4ac. That is 4 times 1 times 13. That is 52 all over 2a. We will have 3 plus minus, what is 36 minus 52? Negative 12. Or negative 12. Or in this case, right? Square root of 12i all over 2. Square root of 12, you can turn that into square root of 4 times 3. Square root of 4 times 3, what you can do with that 4 is that you can get it out of the square root, and you can turn this thing into square root of 2 square root of 3 I divided by 2. So your values are now imaginary. 3 plus minus square root of 3 I. Wait, what is that? Wait a second. Is that right? Wait, did I do this incorrectly? I'm... Is this not... Is this not supposed to be just... Hold on, wait. I'm getting some bad feelings over here. 13 times 4. Am I getting ahead of myself? No, that is 52. 52 minus 36, that is... Oh, it's 16, not 12. Oh, sorry. Okay. Right, sorry. Yeah, I was getting bad vibes because I was trying to get the answer already from my brain in here. So this is actually negative 16, which we could turn into square root of 16i over 2. Square root of 16, of course, is going to be 4. So if you divide 4 by 2, you will get 3 plus minus 2i instead. There you go. That's much better, right? That's what I was expecting. But now, if we're going to remove the plus minus, what we'll have in here is basically 3 plus 2i and then 3 minus 2i. How are we going to do this, right? What is the answer here? Is it y is equal to a e raised to 3 plus 2i times x plus b e raised to 3 minus 2i times x? Well, in some ways, yes, this is kind of the answer, but right, this is very unsightly, right? The appearance of the I in here, right, just makes it seem like, well, this is not a very well thought out kind of solution. In fact, there is a better way to understand this, and we should just wrap this up in the original form of 3 plus minus 2i. In this case, right, even though this is kind of okay, right? This is kind of okay. It's still a bit questionable because now there's a much more elegant way to put this. Let's now try and decompose these two. This 3 right here, this is what we call the real part. And this 2 right here, the thing that is attached to the imaginary number, we will call the imaginary part. What we're going to see if we have, right? If we have answers that are complex or at the very least are imaginary, what we will do is we will have something like this. Y is equal to a times e raised to the real part of x, right? The real part, or basically this is just a number, right? A real part times x, and then we multiply it. Actually, we don't need this right now. We need this later on. Let me retry that. E raised to the real part times x, and then you multiply with a cosine imaginary part, and then plus b sine imaginary part, and then x. That is what's supposed to happen, right? These things are supposed to act as constants for your exponential, because this one is the real part, and then your imaginary, right? Because this one is your imaginary part. If you want to know why, I recommend that you look through Euler's formula. Euler's formula is basically something like this, right? Euler's formula is basically, if you have an e raised to I x, what you will have is basically cosine x plus I sine of x, right? That is the what do you call this? That is the hint. If you want to go any further, of course, I recommend you just go and try this out for yourself. Try and expand these two, right? Hopefully you will be able to see that you can have them merge into this whole structure. So now, right, without further ado, our formula, or rather our general solution for this, will be e raised to the real part, which is 3x, and then a cosine, and then the imaginary part, which is 2x, plus the sine of 2x. Notice that these two always will come in pairs. If you have a cosine, you will have a sine somewhere else. And that makes sense because, well, these are two solutions, right? These are two solutions and they correspond to them having two, right? Two arbitrary constants. So that is for your imaginary roots, right? So just to get what do you call this? just to summarize before we go to the last part, right? Before we go to the last part, I'd just like to summarize that what will happen now if you have a real part, right? If you have a real solution, right? If you have two real solutions, what you just do is the normal e raised to something something x, and then e raised to something something x. That's it, right? A, E, blah, blah, blah. Now, if it's two repeated reals or just one real solution, what you're supposed to do is introduce, right, a linear combination, bx e raised to blank, blank, blank x. And now, if both of them are complex, right, what you should just do is e raised to real x times a cosine blah, blah, blah x plus b cosine blah, blah, blah of x. And so now, we will go to our final example, right? We will go to our final example. I realized I can't have that because it's not green, but we will have something like this. So I will switch the, what do you call this? There you go. I'll switch the, oops, this should be negative. Oh, actually, yeah, there you go. That's better, okay? So now I'll do this. And the first thing that you might see is that, wait a second, this is now third order, right? Well, nothing much changes, right? If we detect the formula, or rather the pattern from earlier, how many times you derive is the exponent of your differential operator, because literally this is the derivative of the derivative of the derivative of y, right? So that will make it d cubed of y minus 3d squared y plus 4dy minus 12y is equal to 0. And again, right, we can just cancel the y's in our brain, and we are left with d cubed minus 3d squared plus 4d minus 12 is equal to 0. Now, what do we notice with this, right? What do we notice with this? Well, it's a cubic. I can no longer provide, or rather I can no longer, yeah, that's correct. I can no longer provide a solution that is just using the quadratic formula, because this is no longer quadratic. So we have a couple of shall we say, techniques to try and get roots for this thing. The first one that I would recommend is the factor theorem, right? Basically, what you're supposed to do in the factor theorem, right? Factor theorem is, say for example, you substitute a value of d, right? Substitute a value of d into this equation, and it turns out, right, that your d cubed minus 3d squared plus 4d minus 12, in that case, if that does equal to 0, that means, right, let's just say you substitute a value of, I don't know, a, right? A works. So if you do substitute this value, and indeed it does come to be 0, then that means that one of the values of d in here is your value of a. If that sounds very confusing, let's just provide a real life example. Say for example, I will try d is equal to 1. Try d is equal to 1. We will have d cubed is 1, 3d minus 3d squared minus 3, plus 4d, that's plus 4 minus 12 is, that is not going to be 0, right? Okay, so d is equal to 1 is not a factor, right? So let's try now, d is equal to 3, okay? 3 cubed is 27, minus 3d squared is another 27, plus 4 times 3, that is 12, minus 12, would you look at that? That is now equal to 0. So now, that means that one of the factors of this whole d cubed minus 3d squared plus 4d minus 12, one of the factors will be d minus 3. Because it got solved by d equals 3, that means that it must be a factor in this whole equation or expression, right? Now that we know that, we can now apply long division, right? We can apply long division. D cubed minus 3d squared plus 4d minus 12 divided by, right, our value of d minus 3, right? And have I taught this before? Oh my. It seems that I have not taught this before. Okay, so I must be misremembering. All right. So now this is the time where I explain to you how long division works. It works the same way, right? Say, for example, 85 divided by 3. What you can do there is then say 85 divided by 3. How many 3's go to 8? That will be 2. 3 times 2 is 6. And then you get 2. And then 25. And then 25, how many 3's go into 25? There's an 8. So 24. And then 1. Right? So there's a remainder 1. Right? So in this case, this works much the same way, but what you need to do is you need to be able to lay it out all properly. This has the power of 1, and this, because it's a constant, has the power of 0. This is laid out properly because 3, 2, 1, 0. Right? That is how laying it out means. And now in here, instead of relying on everything in here, what we just are supposed to do is, well, just look at the leading term. How many d's go into d cubed? The answer is d squared, right? Okay, so let's just put this d cubed minus 3d squared. It just so happens that both of them get cancelled. So you're not going to bring down anything, right? And then this is plus 0d, right? You're not doing anything. And again, right? What gets brought down here is 4d minus 12. And then in here, what is the leading term? This is 4d. How many d's? Oh, yeah. How many d's are getting into 4d? That's going to be 4. So 4d minus 12, that completely eliminates it. So that means that the rest of this will be d squared plus 4 is equal to 0. As we can see, the values here are going to be d is equal to 3. And if you manage to work out d squared plus 4 is equal to 0, right? Short aside in here, d squared plus 4 is equal to 0. What you can just do is put this on the other side. You will have d squared is equal to negative 4. And if you square root, right? If you square root everything, you will get just d. And then because you square root, you need two values. You will have a plus and a minus. That's square root of negative 4, which is going to be square root of 4i, which means square root of 4 is just 2i. Now, you might be wondering, okay, how do I do this now? Earlier, what you said was where there should be a real part and there should be an imaginary part. Well, there is still a real part in here. It's just that we don't see it. This is actually going to be, the real part is 0. And the imaginary part is, of course, 2. So now we have our 3, right? Our 3 values for letter D, which is 3, and then plus minus 2i. Therefore, our final, right, general solution will be ae raised to 3x, right? ae raised to 3x, and then plus, right, e raised to 0x. What is anything raised to the power of 0? It's just 1, right? So this all just gets cancelled to 1. And then you will have your b cosine 2x plus c sine 2x. That will give us our final general solution of a e raised to 3x plus b cosine 2x plus c sine 2x. If you're going to look back at this, this is responsible for your d is equal to 3. These two are responsible for you having d is equal to plus minus 2i. So that is our final answer. This is a general solution. Okay. So if we can see, right, this is a very useful, right? This is a very useful, what do you call this? This is a very useful tool because it now allows us to treat differential equations like algebraic equations, which is very cool, right? There is a decreased level of difficulty, but you now have to, right? The trade-off is now you have to brush up on your algebra skills and quadratic formula. Okay. So hopefully that is no issue. And one other kind of related thing, right? If we think about it, we are reducing the difficulty by turning a differential equation into an algebraic one, which is this. Also the job of the Laplace transform, but that is for later, right? For now, for next video, we will talk about the method of undetermined coefficients, which bandages one of the main weaknesses of the differential operator, which is you can only work on it if x is equal, if the whole of the right side is equal to 0. It will no longer work if, for example, this is x, right? That is now the job of the method of undetermined coefficients. So that will be for the next video. But for now, I hope you guys learned something, or where you were able to review the differential operator using this video. All right, we'll see you next time.